Video about trying to make some sort of understanding of why the derivative of one trigonometric function is equal to another. So I always find it quite peculiar why the derivative of sine would be equal to cosine. And there are many different ways to go about this, but in this video I'll try using the sine double addition angle identity to show you how that is. So this identity, what does it say? It says that for sine and for two different angles, this is equal to sine of the first times cosine of the second, and added up with cosine of the first times sine of the second. Okay, so what is sine and what is cosine? So for any right side triangle where you have a 90 degree, you have this angle here, let's call it alpha, and our side A, B and C. Then we can say that the sine of this angle is the opposite side, so C over our hypotenuse A. So C over A. And likewise, for our cosine of this angle alpha, it's the adjacent side, so B over A. Okay, so just imagine that we have two triangles instead, and this first has the angle U, and then the second triangle has the angle V. So if you want the sine of both of these angles, then it is equal to this. Okay, that's very just nitty-gritty of how this is derived. Now, we want the derivative of our sine function. Now, what does the derivative even tell us? It's just a quick example of what the derivative can tell us. Imagine you have a car going at some speed. Let's say the velocity is given by the function 2x squared plus 5. Right. If I graph this, let's say we have our starting point 5 here, and 10, 15, whatever. 1, 2, 3. Right, so we will start here and just go, since this function is squared, it will exponentially grow into really large numbers, right? This is not representatory, it does not look like this. But the idea is, when we take the derivative, we want to know the instantaneous rate of change. So I'm saying, I want the speed at which the car goes at, let's say, right here. So the idea is that I take a small value in x, and then I get a small value in y, so I get, let's say, delta y, and then delta x. So this idea is that we take this ratio here, as small as possible. So it's not exactly 0, but it's really, really close. So by taking the derivative of our speed function, we get the acceleration of the car. How fast is it moving at any given point? So writing this in a new fashion, I can say y is equal to f of x. This is just this written in a basic form. And I'm saying, I'm taking a small change in our y, and likewise I'm getting a small change in our x value, delta x and delta y. But I only want my delta y, I only want the small change in y. So how do I achieve this? I can take the y over to the right side, likewise, so I get minus y, but I already stated that y is equal to f of x, so I can say minus f of x. And we are taking, in this example, this is with respect to time. So I want to know the speed at any given moment. So my delta x is my small difference in time. So if I divide this whole thing by delta x, I will now be left with this. So x, and now over delta x. Okay, so now we have said what the derivative is and how do we use this with the sign u plus v identity. You might already catch upon it, but if you see this f, our function outside, and then our x plus delta x is written in exactly the same form as this. So if I want the derivative of sine of x, I can now put sine, which is my f, and we're saying u plus v, which is x plus delta x, and then we get minus sine of u, and all this over my delta x, which is v. So to make it clearer, the x is equal to u, and the delta x is equal to v in this newly written form. Right, so now let's expand this as we learned. So okay, that's not denoted, just we're saying sine of the first times cosine of the second plus cosine of the first times sine of the second, and then minus sine of u, and all of this over v. Right, what's our next step? I think this numerator looks kind of nasty, so let's simplify this. I can see that our sine of u is timed into cosine of v, and we have a sine of u at the end as well. So let me write it like this, sine of u, and then if I time it in, I multiply it into cosine of v, and then also minus 1, I will end up with exactly the same, but just looks nicer. Cos of u, I just factorized it, and then cos of u times, that's a sine of v, and then still over v. Now, in the derivative, we want this v to be as small as possible. That's the whole idea behind derivation. So I am saying I'm taking the limit as v goes to 0. So it's not exactly 0, but it's 0.00000, etc. So I'm taking the limit of both sides of this, first of this, and then of this. So first and then second of this. So I'm taking the limit here, sine of u times cosine of v minus 1 over v, and then plus the limit as v goes to 0 for cosine of u times sine of v over v. Okay, and now you might ask yourself, well, cosine of v, and v goes to 0. So we get cosine of 0. So we get an angle that is equal to 0. What value does that give us? So to understand this, we have to look at something called a unit circle, which is trivial in trigonometry. So this quick sketch will do it. So imagine we have a right side triangle here, and we defined earlier what the sine and cosine of this angle is. Now imagine I'm making this triangle so small down here. For this triangle, no matter how it looks, if it looks like this, this, whatever. Okay, no, not like that. It felt like this. So whatever. The hypotenuse, the longest side, will always have a value of 1. So, what does that tell us about this? It says that, okay, so the hypotenuse is always 1. But if the triangle is basically quite even with our x-axis here, shouldn't the adjacent side always also be equal to 1? Yes, it should, right? So if we defined cosine as of this angle which goes to 0, so our triangle must also just, the hypotenuse must lie over the adjacent side. So we can say that cosine is our adjacent side, which is now equal to 1, over the hypotenuse, which is always 1. So cosine of 0 will give us 1. And likewise, sine of 0, this opposite side will be non-existent, right, in this triangle. So if we define it as the opposite side over the hypotenuse, it will be equal to 1. So this is over 1, which is equal to 0. But sine of v, if we have sine of 0 over 0, this is equal to 1. Now that's another theorem for another day, but that gives us 1. So one final step is that we take the limit as v goes to 0. So what about our sine of u and our cosine of u? What happens to those? We can set those outside. So I'm saying sine of u times the limit as v goes to 0 for cosine of v minus 1 over 1 plus cosine of u times the limit as v goes to 0 for our sine of v over v. Now we found out that this, so cosine of v was equal to 1. So we get sine of u times 1 minus 1, that's over v, plus cosine of u, and this, the theorem here says that sine over 0 gives us 1, and this will be 1 minus 1, which is 0, and v goes to 0, but it's not exactly 0, because if it was 0 it would be undefined, but 0 over some really small value, even though it's 0.0000, etc., will give us 0. So I will get sine of u times 0, and this will just cancel out, anything times 0 will cancel out. So you're left with cos of u times 1, which is just cosine of the angle u. But if you change back, I said that x is equal to u, so we get cosine of x. And so I have showed, by using the sine double addition identity, that the derivative of sine would be equal to cosine.